In this video, we're going to take a look at some problem solving with friction. It's going to be horizontal only. So this is sort of a beginning video. Let's take a look and let's imagine that we've got, some kind of simple object like this. And we'll give it a mass, so 5 kilograms. And then we're going to apply a force. And let's make that force equal to, let's see, the weight of this is going to be 49. So let's give it a nice force of about 60 newtons. And then our question is going to be, if the coefficient of kinetic friction is equal to 0.30, then find the velocity after 10 seconds. Okay, so that's a that's a decent problem. So we really should fill in some of the more details about all the other forces that are acting on this object. So obviously the object has weight. So the force of gravity is equal to mass times gravity, where gravity is equal to 9.8. We used to call that acceleration due to gravity, but now we use a slightly more mature word for it, which is the value of the gravitational field at the surface of the Earth. And so the force due to gravity is going to be equal to 5 times 9.8, which is 49 newtons. And then there's the normal force, which keeps us from falling. And a normal force is always present when something's resting on a surface. And that's going to give rise to friction. All right, so look at all these different forces. These are really common players. They're like the cast of a play that shows up, and every scene might be different, but we have similar characters. So we write F with a subscript indicating what kind of forces. And there's also a special relationship between these two, right? So I would call the normal force the lesser known but big brother to friction. So everybody knows about friction, but what we model friction on is the normal force, which makes sense because the normal force tells us how hard these two surfaces are pressing together. So our connection, our relationship between these two brothers, sisters, cousins. So the force of friction is equal to the coefficient of friction times the normal force, and that's always true. So that deserves a little highlight. This is always. They're bound together. So if you know one, you know the other. So in the next piece of problem solving is that F net, which isn't a force all by itself, but it's a constructive element to remind us what to do. So when we apply Newton's second law, it's important to remember that on this side of the equation, we're going to take a look at the forces and how they act together. Sometimes they're going to help each other, and sometimes they're going to work against each other. So this is the effect, or rather, this is the cause. Sorry. And then this is the effect over here. Here's what happens because of these forces. So I have 60 newtons positive pulling to the right, and then I have friction pulling back. And that's going to be equal to the mass, which is 5, times whatever the acceleration is. And then once I get the acceleration, I can multiply by 10 seconds to get the velocity at that point. Okay, so our coefficient of kinetic energy is 0.3. So this is going to be 60 minus the coefficient of kinetic friction because it's moving times the normal force, and that's equal to 5 times A. And then I can put in what I know for numbers. In this case, the normal force, since there aren't any other vertical forces acting, is going to be equal to 49 newtons. So this will be 60 minus coefficient of friction 0.30 times 49, and that equals 5 times A. So we'll do this step on the calculator. Okay, 60 minus 0.3 times 49, and we'll get a number for that. So that's 45.3. Now this is what the net force is. But F net it by itself is not really a force. Okay, equals 5A. So A equals, use a little bit of space over here. A is going to be equal to 45.3 divided by 5, 9 and some change, so about 9.1 meters per second squared. And then the velocity is from a kinematic equation, v0 plus acceleration times time. If we assume it was initially at rest, then I'm just going to multiply acceleration times 10 seconds. And so that's going to be 91 meters per second, pretty fast. Okay, so part 2. Now, the 60 newtons goes away. And the prompt would be find that distance it takes to stop. Okay, well, F net equals ma. You know, as we've mentioned many times before, knowing where to start is probably the most difficult thing about physics. But that's why if we have nice solid places to start, that's excellent. So again, cause of the motion over here, effect over here. And so the cause is just friction, right? So it's only friction that's acting on this. And that's how come it comes to a stop. So this is going to be equal to the coefficient of kinetic friction times the normal force. It's equal to mass times acceleration. Now I can start putting in some numbers. So minus 0.3 times the normal force, which is still 49. And that's equal to 5 times A. So A is going to be equal to, I multiply these two numbers together, 14.7. So that is your force of friction. And then I'm going to divide that by 5. And I get 2.94 meters per second squared, but not quite yet until I put the minus sign in, right? So it's going to be slowing down. And then if I use the kinematic equation where v squared equals v0 squared plus 2 times the acceleration times delta x, and I can put some numbers in. So the speed was 91 meters per second squared. And then the initial velocity, whoops, sorry, that's wrong. The final velocity is going to be 0. And then the 91 is the initial velocity squared plus 2 times negative 2.94. And then x is what I'm looking for. All right, so let's just continue the work there and finish this up. So 91 squared is 8,281, so 0 equals and then 2.94 times 2, and we have a minus sign, 5.88x. And now to solve this, we're going to bring this over to the other side of the equation and then divide both sides by x, or by 5.88 rather. Yeah, so it's going to go pretty far, over a kilometer, not quite a mile though. And we can round it off there, and that's in meters. Yeah, 91 meters per second is quite fast. So that's going to be like around 190 miles an hour. And so that's not very much friction. It's going to take it a while to slow down. Okay, great. So we had a chance to look at when friction is competing against something, but also when friction is just acting all by itself, which is totally possible.